Hello students, welcome to NEET-UG Academy, and this is Kenny sir once again back with my 10 more electrostatics questions as I promised you, and let's start doing it. Okay. Our next sum is I have an arc over here like this, and this arc is subtending here angle of 60 degree. For that you can solve it, but won't have time so much to take a element dx over here and then take a angle like this d theta, and you have to solve it. That means this side it will be cancelled out, and you have to do those calculations, but no need of doing such a way. Just if you have a ready formula for that, it will be better. So for that we have a ready formula for an arc. Remember that if an arc subtend an angle theta, and this is a charge density of linear charge density of lambda coulomb per meter, and this is just the radius r. The electric field at this point P will be directed like this way. This will be like this electric field, and this electric field value will be equals to lambda by into sine theta by 2 into 2 pi epsilon naught r. But that's all. This is the value. So in this case it is 60 degree. So just apply this formula and we will get it. Here also the electric field will be in this direction, that direction, and the electric field will be equals to lambda sine 60 degree divided by 2 into 2 pi epsilon naught, and the radius is, let us take this radius as your r or easy part, calculation part. So you can say this is your r, so it will be lambda sine 30 degree by 2 pi epsilon naught r, and that will be lambda by 4 pi epsilon naught r will be your answer. That's all. Here is our next sum. Here you see there is an infinite linear charge density over this side. Basically you can call from here to here it is a semi-infinite, because it is the end of the infinite linear charge density over here. There is an arc, quarter arc, and of radius r, and this side radius r. This quarter arc is over here of lambda coulomb per meter, and this is lambda coulomb per meter also density, and here is also a semi-infinite linear charge density of lambda coulomb per meter, and here it ends. That means it is also a semi-infinite long linear charge density, and our point is P here, perpendicular to this at a distance r. From this distance it is also r, and from quarter circle you have a radius r. This is the thing. So here to find out we have to find out the electric field at this point. So to find the electric field at this point, once again let us revise what is the net electric field due to the semi-infinite long wire. So semi-infinite long wire, if you want to do it, it is very easy. Just you have to apply this formula. This is this is our semi-infinite long wire, and I am here. No, sorry, it is too high. Here it is semi-infinite linear charge density. This side it is going to infinite, and I am at this point P at a distance r. Let us think it, and this angle that it is making is your theta 1, you can call it. This is theta 2, you can call it. So you know the formula for our Ex the formula, and then it will be your Ey at this point. So Ux is equal to k lambda by this distance is your r into cos theta 2 minus cos theta 1. So it will be k lambda by r. Cos theta 2 will be your 0, because here theta 2 is equal to 0 and theta 1 tends to 90 degree. As this approaches infinite, this angle tends to 90 degree. So it will be cos theta 2 means cos 0 minus cos 90. Hence it will be equals to k lambda by r, Ex. Next is our Ey. If you find Ey will be equals to k lambda by r into sin theta 1, that is sin theta 1 is 90 plus sin 0. So it will be your k lambda by r, it will be. So that means the electric field, net electric field will be equals to root over Ex square plus Ey square, that will be your k lambda by r whole square plus k lambda by r whole square and square root of it. That means you will get it k lambda by r into root 2. Just please remember this value for, and the resultant will be this direction of a semi-infinite long wave at this point P. Perpendicular distance is your r from that semi-infinite long wave. So if I erase this thing, I will have this result k lambda by r root 2, remember it. So once I have this k lambda by 2, so let us think this part is, let us name this as AB, and this part let us name it as CD. So due to this AB, the electric field at this point, due to this part only AB I am telling you, due to this part AB, the electric field will be like this, EAB resultant, and this EAB, just now I have found it out, will be equals to nothing but k lambda by r into root 2. Same way for this ECD, if I think it over here, it will have an electric field in this direction, ECD, same way that I have found it out, will be equals to k lambda by r root 2. So you can see this k lambda by r root 2 and k lambda by this one get cancelled out. That means this is 0. That means E net EAB minus ECD will be 0. That means along this direction there will be no electric field. So the only electric field will exist due to this quarter circle. This electric field exists, and just now I have given you the formula, previous sum I have given you the formula for the electric field due to the arc, and that electric field due to this arc will be equals to, you know the formula, that is equals to lambda by 2 pi epsilon naught into sine theta by 2, and this distance is your r, that's all. But here it is, you know this angle is nothing but 90 degree. So here you put in 90 degree, that means it will be lambda sine basically 90 by 2 pi epsilon naught r will be equals to lambda by 2 pi epsilon naught r into root 2. So this will be your answer. This is our next sum. This is a very simple sum. The simple derivation. Find the electric field inside a uniform charge density. Uniform charge density or charge density rho. And inside the sphere, you see, inside the sphere, everywhere the charge is, everywhere there is a uniformly distributed charge is there, and the charge density is rho. I have to do this topic, otherwise my your concept will not be clear. That is why. So to find the electric field here, think it P. So what I have to do, I have to pass a Gaussian surface through this point P, which encloses this volume. Now, according to the Gaussian law, we know that the flux that is coming out of this Gaussian surface is equal to how much charge it is enclosed inside it. So how much charge is enclosed inside it will be equals to how much? 4/3 pi. If the radius of this Gaussian surface is your r, it will be volume will be r cube, and the charge density is, as I said to you, it is rho. So here the charge density is rho. That is the charge that is enclosed inside it is equal to 4/3 pi r cube rho. And this is nothing but the total charge that is enclosed inside this Gaussian surface. Because I want to find the electric field at this point P, so through the point P I will pass a Gaussian surface which encloses some amount of charge that is within it. And what is the charge within it? That is this much. And we know the rule of Gaussian surface, that is equals to the charge enclosed divided by epsilon naught is the flux. The flux that is coming out of this Gaussian surface is equal to Q by epsilon naught. So Q is how much? Our 4/3 pi r cube rho divided by our epsilon naught. And what is the flux? In the form of the flux, what you write? Flux, you will write the uniform electric field that is throughout it, that is E, into the area of the surface area of this sphere, that is equal to 4 pi r square is equal to 4/3 pi r cube rho divided by epsilon naught. So it will be equal to 4 pi, and this 4 and this pi will get cancelled, this r square r get cancelled. So it will be electric field will be equal to rho r. What is electric is rho r divided by 3 epsilon naught. That is the electric field. You will get it. So electric field at the point P will be equal to rho r divided by 3 epsilon naught. Remember it. That's all. This is another sum. In this sum, you can see it is given a non-conducting. Remember it is given non-conducting uniformly charged sphere of charge density. How much it is? Rho. Rho is the charge density of it. Is there a cavity of radius b? Cavity of radius, how much b is cut off from it, whose center is at a distance of a unit from the center of the larger sphere. What you have to do? You have to find the electric field inside the cavity, and you have to find the electric field outside the cavity but inside the larger sphere. Okay. Just now, you see this is our sphere, and this is the center of it, and in the center there is a large cavity is there. That, as I told you, and this cavity's radius is, as I told you, it is b, and the distance between the center is your a. Take this away. I want to find the electric field inside the cavity at any arbitrary point p inside the cavity. So from here I am drawing a vector. This is the direction of the electric field due to this uniformly charged sphere plus, and from here another direction will be there. Let me explain you what it is. Actually, first of all, this I will think it that there is no cavity is there, and since there is no cavity, so this larger sphere, as I taught you in the previous, that larger sphere with a uniform charge density can create an electric field. How much? I told you that E will be equals to, it is equals to rho r divided by 3 epsilon naught. You can see it in my previous derivation, where I explained you how the electric field inside a uniform charge density is equal to rho r divided by 3 epsilon naught, where r is the distance from the center of it. So first I will think it that there is no cavity is there, anything is there. This is the uniform charge sphere of charge density rho, and according to that I will find out what is the electric field from the center O, and by this r. That will be the E1 thing. Next I will think it that since I am taking out the cavity, and I have already counted this as without the cavity, so I have to think this cavity as a charge sphere of a negative charge sphere of charge density rho. and I will find it due to this negative charge density what will be the electric field. This cavity is applying at this point, and by adding those two electric fields I will get the net electric field at this point P. So let's do it. So electric field at the point P will be equals to electric field due to the positive charge density at this point is E1, and electric field at this point due to this negative charge density at this point P, I am taking it as E2. Now E1 will be what? But I already told you it is equals to, I have derived it in the last derivation, I have derived it already. It is rho R divided by 3 epsilon naught plus electric field due to this negative charge density at this point will be what? E2, and that will be equals to negative R, and that this distance let us name it as C. So it will be equals to C bar divided by 3 epsilon naught. So it will be equals to rho divided by 3 epsilon naught, and the bracket will be your R bar minus C bar. So R, as you know that this is a triangle law. So in the triangle law we know that vector A plus vector C is equal to vector R. But the vector A will be equal to vector R minus vector C. So this thing, if I apply over here, so you will get it rho divided by 3 epsilon naught, and this is your constant A. Fine. And this proves that the electric field inside this thing is constant. That's all. Now what I have to do? I have to do the next one. Find the electric field outside the cavity anywhere here, but inside the larger sphere. For that, I have to erase this. So please take a screenshot of it. Okay. So this this cavity was there, and this is the point, and I have to find the electric field at this point outside the cavity here, and this distance you know this is your vector A. Again let us think this vector is your vector C, and this is as a vector R. Let us take it. Now again I will think it that this is creating an electric field, thinking that there is no cavities there. So for that means electric field at the point P due to this bigger sphere will be equals to, that is total electric field, that is will be E1, and the electric field at electric field 2 E2 means the electric field due to this negative this cavity will be creating an electric field at this, but this point now is outside this cavity, remember it. So when you take the electric field outside a charge sphere, what it will be, that I have to show you. First let us write it down. What is the electric field due to this at this point? That will be already that we know that it is because this point is inside this uniformly charged density. So it will be rho into R divided by 3 epsilon naught. But for this E2 I have to calculate separately, because E2 you should know that how to do this E2. Let us do it here. Think if this is our charge sphere. This sphere is this one. Of volume charge is your volume is this radius is d, and this distance, you think if this is our p. So to get the electric field at this point P, what I have to do? I have to pass a Gaussian surface through this point P, and this has a how much negative charge density, and this distance is what? This distance I am taking is as t. Think it. So E2, in place of E2 that I can write it rho R divided by 3 epsilon naught plus E2. What I am writing at the part E2. Let us find it out E2. Then I am writing it. So to get the E2, to apply Gauss's law, because since I pass a Gaussian surface to this point P, the area of this Gaussian surface will be equals to E into 4 pi r square matlab c square is equal to the charge enclosed in it, that is 4/3 pi into b cube into density divided by the epsilon naught. This is the volume of this thing and this is the charge density, that is called negative charge density, and divided by epsilon naught. Now if I cancel out this 4 pi, this 4 pi, then the electric field I will get it equals to, little bit cautiously I have to do it. This is, you can see this as BQ is here and this is negative because due to this negative charge, and C square is here and the epsilon naught is here, right? So that one I have to write it down here, minus BQ into density divided by C square into epsilon naught. But I have to give a vector also, unit vector along it. That is C vector I have given it. Okay. So now to make this C vector clearly, because these are just found out, this C vector, now C vectors, these are given the unit vector. So rho r divided by 3 epsilon naught, this will be now minus, it will become minus b cube, rho b cube divided by, in place of the C vector I can write it vector C divided by C into C square into epsilon naught. That means finally it will be rho r divided by 3 epsilon naught minus rho b cube divided by epsilon naught into C cube, that is the magnitude of the vector C is C here and the vector C. And in place of the vector C I can easily write it as vector r minus, this is, you can see you can write it r minus vector E. That's all. In place of C you can write it. This is r minus, that's all. This is the sum. In this sum, what is there? There is a ring of radius r, hollow ring. This is a ring of radius r, and there is a charge plus q is kept over here, and there is a charge minus q kept over here. And the distance from here it is L, and from distance here it is your L. What is asked here is to find the total flux. Find the total flux that will pass through the ring of radius r due to this plus q charge and this minus q charge. So to do this sum, we can do this sum very easily if we have an idea of solid angle. We have an idea of solid angle. What solid angle idea you should have, that how the solid angle is related with the apex angle of a cone conically. So let us do that. I am showing you, that will be very useful for you in the many problems. So you can check it how the apex angle, like conical angle and the solid angle, how they are connected with each other. So for that I need a small derivation. So that I am showing, because how, let us do it. So see, this is a part of the sphere, think it. This is a part of the sphere, and this part of the sphere is subtending here, think it, a conical angle of, this conical angle, not this solid angle is, think it, omega. And if I think it is a plane angle, that's or conical angle, whatever you call it, this angle is your theta. How this theta is connected with this omega, if you know, it will be very useful for you doing any kind of sums. In your flux, generating flux, and the sums that are connected with the flux, you can see it. That let us do try and find the connection between theta and solid angle. So for that, what you have to do, you take a thin ring on this curved surface, because from here to here this is our curved surface, and so this curved surface is subtending at here the angle. The ring is actually subtending here the angle sorry, I am just ring, the ring that I am, the elementary ring on this curved surface I have taken, whose thickness I am assuming it as dx, and which is at a distance x from this vertical line, and this is the radius of our sphere r, and this is also the radius of the sphere r, and this angle, this elementary angle is your, you think it is d alpha, and from here is the angle you think it is alpha, right? So you can see, so what is the area of this ring? So area of this ring, if I think this area of this ring is dA, that will be equals to the circumference of it, that is 2 pi x, into the thickness, that is dx. Now you should know that this 2 pi is here and this x is opposite by hypotenuse, so this you can say it is equals to this x is nothing but actually is equal to r sine alpha. This much is x is equal to sine alpha. So I can put it in place of x, I can put it r sine alpha. And dx is equal to, I can say, is equal to r d alpha. So this is your r d alpha dx. So this is the area of this elementary ring. Now like this, millions of rings are there to form this curved surface area. So that means that is equals to, let us make it simplified, r square sine alpha d alpha. Now if I integrate this, so if I integrate this dA, so here you can see it is 2 pi r square sine alpha d alpha. That means it is equals to 2 pi r square integration, where to where I have to do it? From alpha, from 0 to theta. That means it will be 0 to theta. So 0 to theta, if I integrate it, I will get the area of all these rings from here to here, because from here to here it will be that much we have to do. That is 0 to theta, that is equals to sine alpha d alpha, and this is your r square. So it will be equals to 2 pi r square, it will be minus cos alpha. So minus cos alpha will be equals to 0 to theta. That means if I put cos 0, it will be equals to, when I cos theta, then it will be equals to 2 pi r square minus cos theta plus that will be equals to cos 0. That means it will become 2 pi r square into 1 minus cos theta. Let us take it this here. This one, let us take it here. I am doing it. So area I have got it because to 2 pi r square 1 minus cos theta on the basis of the flat angle theta. Now if I do it with respect to that solid angle, so with respect to the solid angle, I know that the area of this thing is r square, here I am doing it, r square into omega is the area, and area in other way I have got it 2 pi r square into 1 minus cos theta by taking this as a half angle, this conical, this apex angle as half angle, theta I have taken this, I have got this area 2 pi r square into 1 minus cos theta. So this I can put it equals to 2 pi r square into 1 minus cos theta. So you will see that here. So here there is r square and this r square get cancelled out. So it will be solid angle will be equals to 2 pi into 1 minus cos theta. So that's all. So this relation, this solid angle and this half angle, this relation, you can say this angle as a flat angle, apex angle, whatever it is a flat angle basically. You can see this flat angle relation and this solid angle relation will be helpful for you in many sums. So here I am using this, in this sum I am using this relation. So you will see that due to this relation, this sum will become 50% easier. If you want to do it in the other way, it will become very difficult. So let's do it. So for this positive plus q, you can see this plus q is from this flux Q, total flux that is emerging out of it in the order direction is equal to, it is equals to, total flux will be equals to Q by epsilon naught. And Q by epsilon naught, it is spreading, this flux is spreading in the throughout the dimension, that is equal to, in the solid angle of 4 pi. This total solid angle is, is equal to 4 pi. That means for the 4 pi solid angle, this Q is giving out, how much flux it is giving out from all the direction, that is giving out equals to Q by epsilon naught. But how much flux I want through this ring is this much, and let us think this angle is our theta. So now you understand what will be the issue. This Q is emanating, this spreading out the flux in the 4 pi dimension is equal to Q by epsilon. But I want only in this much dimension, this much solid angle I need it, and this half angle where the half angle is theta. So for that, for here for the 4 pi solid angle, you see it is the flux is Q by epsilon. For one, it will be equals to Q by 4 pi epsilon naught, and for this our omega, the solid angle, it will be equals to Q omega into 4 pi epsilon naught. Understood? Now this omega, according to this relation, will be equals to, that means the total flux that is going out due to this positive will be equals to, that is flux due to this positive Q will be equals to Q into omega by 4 pi epsilon naught, and that is Q is that omega is equal to 2 pi into 1 minus cos theta divided by 4 pi epsilon naught. You understand? So now you see this 2 pi and this 2 pi get cancelled, only 2 is there, cos theta, let it be cos theta over there, let the cos theta over there, then I can easily calculate the cos theta, because you know that this is R, this are taken as L, so this hypotenuse is nothing but actually root over R square plus L square. So cos theta is very easy to find it out here. Cos theta is nothing but actually is here base by hypotenuse, that is L by root over R square plus L square, and we can replace it, but let's do it. The final let us do it. Q into, we get it for the Q into 1 minus cos theta divided by 2 epsilon naught. That is the flux due to this positive passing through this. So and flux due to negative also is passing through this in this direction. Because the electric field due to negative is actually towards it, and electric field due to the positive is away from it. That means the total flux actually passing through this and actually passing through this will be in the same direction. They will be added. You understand? So it will be added means the total flux will be equal. So therefore the total flux, I can say this total flux here. I can write it over total flux. Total flux will be equals to, that is I can say this phi is equal to 2 times of this basically. That means it will be twice of phi of positive one. That will be equals to 2 times of it, because one for the positive, another for the negative, and they have the same value. So this is why. So it will be 2q into 1 minus cos theta divided by 2 epsilon naught. So here 2 and 2 get cancelled, so it will be equals to q by epsilon naught, and in place of cos theta just I can replace, that is equals to L by root over R square plus L square. That's the thing. So it's over. In this sum, it is given that there is a plus q1 charge over here and there is a minus q1 charge over here. So here the electric field that is being spreading out here at an angle of alpha, that means the flux that is spreading out basically at an angle alpha is being received by this minus q1 at an angle beta. Now they asked you what is the relation between this alpha and beta. When this is being projected at an angle alpha maximum, but in between there is other electric fields also, that is basically here the flux that is being spreading out at an angle alpha of half angle alpha of this conical way will be received by this minus q1 same way at an angle beta. Now they ask you what is the relation between this alpha and beta. So for that, the last sum what I explained you is that I have explained you what is the relation between the solid angle and the flat angle. So this is the relation. So this relation I will use over here. Here you see the flux that is being spreading out from here at an angle alpha will be received by this charge at an angle beta. So the same flux will be received by this plus minus q1 at this angle flat angle beta. That means flux, you can say that flux emerging, and you can say the flux from q1 at angle alpha is equal to flux from q2 at an angle beta. So you see that flux is for 4 pi, the total flux, the 4 pi from a charge, the total flux for a 4 pi is equal to how much? Equal to q1 by epsilon naught. Therefore for a solid angle, think it this solid angle, it will be equals to how much? It will be q1 divided by 4 pi epsilon naught into this solid angle. Again I am saying for the solid angle 4 pi, the flux for a given charge we should know is equal to q1 by epsilon naught. So for 1 unit it will be q1 by epsilon naught divided by 4 pi, unitary method just. And for the solid angle this omega, it will be q1 into omega divided by 4 pi epsilon naught. So here also I can write it this. So it will be q1 into this is the solid angle same this 4 pi epsilon naught. And here it will be equals to q2 solid angle into this is 4 pi epsilon naught. Okay. So now you see this 4 pi epsilon naught and 4 pi epsilon naught get cancelled out. So it will be equals to q1 into this solid angle 1 will be equals to 2 pi into 1 minus cos alpha will be equals to q2 into 2 pi into 1 minus cos beta. I think so beta and alpha I have given it. So alpha and beta it is. So it will be 2 pi and 2 pi get cancelled, and you know 1 minus cos alpha is equal to 2 sin square alpha by 2. So it will be q1 into 2 sin square alpha by 2 is equal to q2 2 sin square beta by 2. So you get 2 and 2 get cancelled, and this is the relation between alpha and beta. That's all. So you see that if you know this relation, that is how its solid angle is related with the flat angle, then your many problems can be solved very easily. So this is the thing I want to give you this knowledge with the help of the last one sum and this another problem. So please follow them very carefully. Okay? This is our next sum. In this sum, this is a conductor, a metallic conductor, and in this metallic conductor you have a cavity. You have a cavity, and inside the cavity you keep a charge QB. There is another cavity is there. Inside that I kept a charge QA. And remember, this is a conducting sphere. So no electric field can happen here. Electric field inside a metallic conductor is 0. Remember it. And inside this cavity QB is the charge QB is there, and there is another charge QA is there. So how to deal with these kind of situations? Let us do it. So you will be able to understand after my discussion. So there will be no problem, I think so. First of all, you have to find the electric field. This is why I set up the questions like that. So your concepts will be clear. Find the electric field at the point A. And I have to find the electric field at this point A. Yeah, electric field at the point A will exist. Remember it. Because through the electric field, if I pass a Gaussian surface, it encloses this. If this QA is symmetrical, it may be symmetrical, may not be symmetrical. Let us think that this QA is at the center of this Gaussian surface. So if I pass this to the Gaussian surface, that means the electric field at this point A will be it happened to be, if it is symmetrical, and if this QA is kept at the center, then electric field at this will be equals to, you know that it is QA divided by 4 pi epsilon naught, and if this distance is, you know, it is equal to, you think it r, so it will be your r square. So electric field at A, I have found it out. That means electric field at A exists, remember it, inside the cavity due to this charge. There is no problem. Next question is, find the electric field at B, this point. Let us consider for this charge, if there can be electric field here or not. So what happens, you know that QA will induce a charge minus QA over here. And if I spread this minus QA evenly, think it, let us this QA as the center of this. So let us think it minus QA spread symmetrically. Then we can say that the charge density, you can call it this as the charge density, and that charge density you can call it as sigma A. And sigma A, this I am going to sigma A, you can call, if this charge density, that means this minus Q will be induced on this surface, due to this charge, and you can spread this charge QA evenly throughout this surface, and you will get this surface charge density sigma A. Sigma A will be equals to nothing but it will be QA minus QA divided by 4 pi. Let us think if the radius of this cavity is let us take this B, so it will be B square. It's not sigma A is this. Same way, another, due to this plus Q, also on this surface, the minus Q, net total minus QB charge will be induced on it, on this surface. That means you see that minus, and if you want to find the surface charge density on this will be equals to, surface charge density on this will be equals to, you can call it as a sigma B, will be equals to minus QB divided by 4 pi. Let us think the radius of this is your C. So it will be C square. Now what was our question in this part B was there, that is there any electric field at this point? Now if I pass a Gaussian surface through this, enclosing this, you can see that the Gaussian surface encloses minus QA charge and plus QA charge. So no electric field. So that means electric field at B, either it is uniform or non-uniform, there is no question first of all, because there is no electric field. If it is at the center, that the uniform electric field or non-uniform electric field, after that one will come. But in this case there is no electric field, because it do not, this Gaussian surface, that is the total flux that is coming out of this Gaussian surface, will be equals to 0. That is why it is 0, because it is QA minus QA divided by epsilon naught. That means there is a charge QA and there is an induced charge minus QA, and this is why no electric field is passing through this way. If you consider to this side also, you see that if you consider another Gaussian surface through this side also, which passes to the point B, in that way also you see that there is no electric field passing through this point B, because this plus and there is a minus, So total net charge inside this Gaussian surface is 0. So there is no electric field coming out of it. That means this QA cannot create the next. I am coming to the number C question. This question is over. Under this B is over. There is no electric field at point B from both the sides I showed you. Now for the C case, find the force on QA on B. QA on B. Find the force on QA. Find the force on QA due to QB. The force on QA means, let us name it actually I have written it small. Let us make this as the small QA, and let us make this as the small QB. So this QA is not creating any force on this because this cannot apply any electric field at this point only. Because you saw that it is not crossing here. Because this minus QA charge will induce another charge, not here, but it will charge outside it. That means this minus Q actually will induce another plus QA charge over here, and this surface minus QB charge will induce another plus QB charge over here. So you see that this is why this charge QA and this charge QB are not interacting with each other, because no electric field is coming from here to here and no electric field is coming from here to here. So only they are this minus QA charge will induce another QA charge outside it, and this plus QB charge outside it. Now if this charge QA is uniform, you just spread it out symmetrically and you get this divided by 1. If you think this, you can call it as you can spread it this uniformly and you can get the surface density of it. Now this charge can create a force on this Q. So our next question is find the force on Q. That force on Q, if actually there will be a force on Q, but it cannot be given exactly what is the force on Q, because this charge is not exactly uniformly distributed. But there will be a force on Q due to this charge QA and plus QB, remember it. So it depends on how symmetrically it is being given. So that is, I can just ask you that find the force on, not on the force on the Q. Is there any electric field is causing, is there any force applied on Q due to this system? Yes, there is a force on Q due to this system. So that's all for this sum. This is our next sum. This is a very famous sum, and this is, everyone asks me this about this sum. So what is actually, there is two metallic plates are there. One is charged with Q1 and another is charged with Q2, and the question is asked that what will be the charge in this side plate, inner plate, and what will be the charge in the outer plate. And like these sums, many other sums can be given, in which what I am deriving right now, you can use it as a formula. So let's do it. So let us think that the charge inner one, let us think it, this is charge is Q1. So if I give a charge Q1 over here, so this will be, you take it as Q1 minus Q1. So that this plus this makes it this one. So if this is minus Q1 plus Q1, this is, I am taking it as minus Q1, right? So it will be this is plus Q1, so it will be minus Q1. So because this Q1 will induce a minus Q1 here, and since it is minus Q1, this will become Q2 plus Q1 this side, right? So what I have to do it now, this is a metallic plate. So if I think it like this, if I think it in an enclosed way, that there is, to this metallic, this position, there is what is the electric field at this point P or K, whatever it is. Electric field is how much? Due to this charge, due to this charge, due to this charge, this charge. The metallic, because since this is a metallic plate, electric field here it will be 0. So what will be the electric field due to this? At this point it will be Q1 minus Q1 divided by this plate. It is distributed in this plate. So it will be charge density will be equals to divided by A and then 2A epsilon naught it will be. And this electric field is going this direction. The direction of this electric field is this way. Due to this, remember it. And for this minus plus Q, for this plus Q1, the electric field is positive, so it will be electric field will be going this way. For this, so it will be opposite way. So it will be, I am writing it as minus Q1 by 2A epsilon naught because due to this, okay. Because but this minus Q1, again this has an electric field this direction on this. So it will be basically it will be your plus due to this plus this direction, because the electric field due to this minus Q1 will be this direction for this point. So it will be that will be 2A by epsilon naught. And for this charge it is positive, so the electric field will be this direction towards the K. So it will be minus, because this direction I am taking it as minus, this direction I am taking it as plus. So it will be Q2 plus Q1 divided by 2A epsilon naught, and this is equal to 0. So these things are not required actually. This is, you can cut it. This position, this and this, all you cut it. So you get it QA, Q1 minus Q1, this, which this, you get cut it. So Q1 minus Q minus Q1 plus Q1 minus Q2 plus Q1 equals to 0. That means you see this and this get cancelled out. So it will be minus Q1 and this will be your minus, I think this is minus. So it will be Q1 minus Q2 is equal to minus 2Q, that is 2Q1. That is Q1 basically will be equals to Q1 minus Q2 divided by 2, right? Okay, so that means this side, if I calculate, you calculate here, this is minus Q1 and minus plus Q2 by 2, and if you calculate, you will get it here, it will be Q1 plus Q2 by 2, and this side it will be Q1 means that is will be equals to this side, the plate will have a charge of Q1 minus Q2 by 2, and this side since this is plus, so this side it will get minus Q1 minus Q2 by 2, minus of it, just entirely minus, and this side it will be your Q1 plus Q2 by 2, okay? It's okay. That's all. So you can remember this as a formula. And for the inner one will be Q1 minus Q2 by 2 minus Q1 minus Q2 by 2. And the outer one will be equal to Q1 plus Q2 by 2, and this outer will be Q1 plus Q2 by 2. That's all. This is our next sum. In this sum, there is a linear charge density. You see, this is linear charge density, infinite long linear charge density. This side it is also infinite long linear charge density, and this is a semicircle linear charge density. All of them has a charge density of lambda coulomb per meter. Now, in the previous sum, I already explained you electric field due to this. We have to do. Actually, we have to find the electric field at this point P. Now let us name this as AB, let us name this as CD. So electric field due to this AB part will be this side, right? This is EAB, and electric field due to this CD part will be this side, it will be ECD. Now already I have said to you that electric field due to this semi-infinite long linear charge density at a distance r will be this direction and that electric field will be equals to k lambda by a root 2. Fine. So that means this EAB is also k lambda by, there is a means your arc is there, not a, r root 2, and for this CD also this side it is k lambda by r root 2, and there this is this direction and this is this direction, and the angle between them is 90 degree. You can see it. So that means the electric field net will be along this direction due to this EAB, and E will be equals to root over k lambda by r root 2 whole square plus k lambda by r root 2 whole square. That means it will be root 2 whole square is 2, root 2 whole square is 2, that means it will be your total will be equals to k lambda by r into 4. That means if I square root whole square, that means if I square root it, it will come 2, because it will become 2 k lambda by r. It will come. It is this direction, and again you know, due to this arc, there will be an electric field this direction. Due to this arc, this direction a arc. Already I know the formula for the E arc that I told you. Lambda by sine theta by 2 into 2 pi epsilon naught r, right? So here it is, theta is our 180 degree because it is a semicircle, full semicircle is there. So that means it will be lambda sine, this will be 180 by 2, that is 90 degree divided by 2 pi epsilon naught r. That means we are getting E arc will be equals to lambda, the sine 90 is 1, that means we are getting 2 pi epsilon naught r. And what we are getting from here, it is equals to 2, in place of k I can write 1 by 4 pi epsilon naught r, and lambda is here, this 2 and this 2 get cancelled 2, that means it is coming lambda by 2 pi epsilon naught r. So here you see this is E, due to this side this E is lambda by 2 pi epsilon naught. I am talking about this is E. Let us name this as E resultant. Okay, this E resultant is this side due to this infinite, semi-infinite long linear charge density and semi-infinite long linear charge density. The resultant of ECD and EAB is this side, it is ER, that I have found it out lambda by 2 pi epsilon naught r. Another, due to this arc, it is E arc is this side, that is equals to lambda by 2 pi epsilon naught r. So see, this both of them are equal. So net electric field is equal to lambda by 2 pi epsilon naught r minus lambda by 2 pi epsilon naught r. That is E, basically it is, I am calling it E arc minus E resultant basically, and this is coming equals to 0 because this thing and this thing is cancelled, equal to 0. That means net electric field at this point due to this system is equal to 0. That's all. This is our next sum. What is the potential energy of a uniform charge sphere of charge density rho? That means this is our uniform charge density sphere, whose radius is this is our center, and this radius is your r. So how much energy is required to charge this sphere with a uniform charge density rho? That is the question. That is equal to the potential energy of this system. Just visualize the system. So what for that you have to think it that initially it was charged and let the charge be equals to this much. This much it is charged already. And this charge density, you know, it is equal to rho. So how much charge is there? First let us find it out. So how much charge is there inside it? This, if you think it, so it will be equals to 4/3 pi. If I think this radius is your smaller, so it will be 4/3 pi r cube into rho. That much charge is there. Let us think it, this is our small cube. Now, on this small cube, this is the instantaneous charge of this sphere. When I am charging this sphere from 0 to our uniform charge density rho, think it, the total charge I will give it to q, 0 to q I am giving it. To instantaneous charge at that moment is, this is the small q. At any moment during that, while I am charging it, during that time, at an instantaneous time, instantaneous moment, this charge has a, this sphere has a charge q. On this sphere, if I go now, I have to add some amount of charge around it in a thin spherical shell. Let us, this thin spherical shell, I have to add some charge. This is think it here. And how much work is done to add this charge? Let us first find it out. That is, already you know that there is a charge q, and on that I am adding a thin charge spherical shell on it of how much thickness dr. So what will be the work done? That is the potential energy of this system. There is already a charge that will be equals to, you can call it d potential, du you can call it. So du will be equals to, that is already a charge q was there, and I am adding one charge on it. This is a small amount of thickness of charge, that is 4 pi r square is the surface area into thickness, will give you the volume of that thin sphere into the density divided by 4 pi epsilon naught, and the distance r is there. So this and this get cancelled out. So 1 r is there, 4 pi epsilon naught. So you can see that how much charge it is here. 4 pi get cancelled out. So it will be q rho divided by epsilon naught, and here it is r dr. Okay. So what I will do now, you have to find out this q. This q is equal to, already I have done it, that is equals to 4/3 pi r cube, and it is rho. This is in place of this q, and there is already rho r is there. So rho into r is there and dr is there, divided by epsilon naught is here. So here we will get it equals to 4/3 pi 4/3 pi, then rho square is also there, and divided by, you know, epsilon naught is there, and 4/3 pi rho square epsilon naught. What else is there? R to the power 4 dr is there. So now nothing we have to do. This is the potential energy due to this adding of this thin charge shell. So if I add like this, from shells like this from 0 to this much, then I will get the total energy of this system that I am adding it. So just have to integrate, nothing we have to do. We have already found it out for this adding this thin charge spherical shell. So now we have to do the integration of it. So here I am doing the integration. So that is the total potential energy of the system. That will be equals to 4/3 pi rho square 3 epsilon naught is a constant. 4 pi rho square 3 epsilon naught is a constant. So r to the power 4 dr is there. Integration. How much it is? Where to where I have to integrate? From 0 to capital R. So it is 0 to capital R. That means it will be equals to 4 pi rho square 3 epsilon naught r to the minus this, you just put it first, r to the power 4 by r to the power 5 by 5, sorry, r to the power 5 by 5, and this you just put it 0 to capital R. That means it will be equal to 4 pi rho square by 3 epsilon naught r to the power 5 by 5. This is our total energy of the system. If you want to make it more simplified, in place of rho, we can calculate in terms of the total charge Q. You can also express it. Just have to write it nothing but rho, you have to write it. Rho is equal to how much? It is the Q divided by the volume, that is 4/3 pi IQ. Later on, you can replace this if you want in terms of Q. So here you can replace it. That's it for this one. That's all for today's video, and thanks for watching it. And once again, I will be back with new, more interesting videos. Don't forget to like and share my videos, and if you like more, you subscribe it. So that's all.